So, welcome to this second lecture on structural analysis, and we have discussed certain structures in the last lecture. Today, we're going to solve some problems on truss structure and then frame structure. So, before we start with today's lecture, let me just recall the importance of the studying the subject of statics, because you see, uh, you can find many structures around you that are designed on the principle of static equilibrium, and all their life they basically remain in equilibrium, even though they sometimes support a lot of dynamic loads like column of the bridges, and but still you observe that they always remain in static equilibrium. Similarly, the transmission poles and communication towers, they always are in static equilibrium. So the knowledge and the concepts that you are going to learn in this course of statics will obviously be useful for you in future courses as well. For example, mechanical vibrations, solid mechanics, machine design, dynamics, and other courses related to the design sector actually. So we have actually learned that one of the methods of solving the truss structure is the method of sections, and this is based on the fact that if a truss structure is in equilibrium, then uh, its portions will also be in equilibrium, and we can use the equations of equilibrium to find out the values of unknown. So another important thing related with the truss structure was that I told you that the each and every member of these truss structure will be a two force member, because you see they are always pin connected at their end joints, and whatever loading the truss structure is basically supporting, they are always applied at the joints. They are never applied at in between like this. So you see that here the only external load of 1000 Newton that is acting at point A is actually applied at the joint. It is not uh, applied at any other location like this. Okay, so this will going to violate the truss structure, assumptions of truss structure. And so therefore each and every member, since it is pin connected at both the ends, is actually a two force member, and so there is only one force acting in the member, that is uh, along the axis of the member itself. So the line joining the 2 points, if you remember the definition of the two force member. So these points are important to remember before starting the analysis of truss. So here, this is the problem 6-31 of your textbook, RC Hibler 12th edition, and in this problem, truss structure for a light airplane is shown, and we need to find the forces in this member BH, this member BC, and this member HC. So we have to actually find out the forces in these members. So we have to think of, since we are using the method of section, we have to think of a section that that passes from these members, and that also split the entire truss into two sections. So let's imagine that if we pass the a section like this, it is obviously passing from the member BH, HC, okay, but and these forces are required actually, but in doing so, it is also passing from other members that are actually not needed. And you see, it is passing from 1, 2, 3, 4, 5 members. So we have learned that in method of sections, we should try to select a section in a way that it should only pass from at most three unknowns, right? So I think this choice of selection or choice of selecting the section was not right. So let us consider another section like this and name it as AA dash. So in this way, you see that it is still passing from this member, which is the required member, the required force, this member, which is also the required force, and it is also splitting the member, the entire truss into two portions. So we have now the right hand side, and we have the left hand side of the section, and it is purely arbitrary for us to select any of these. sections. We can consider any of this right hand or left hand section, and then we can apply the equations of equilibrium and try to find out these unknown forces. So you see that if you consider the left hand side, you will observe that you have to find out the values of uh, these reactions first. Okay, the pin reaction. So two pin reactions are acting here, two pin reactions are acting here, and therefore you have to find out the values of these pin reactions if you want to consider the left hand side of this section AA dash. While if you will going to consider the right hand side only, you will observe that we don't need to actually find out these reactions because uh, they are not appearing on the right hand side. Okay, so you only have to consider these known forces and the geometry on the right hand side, and this will going to simplify our work. So the better choice is to consider the right hand side in this problem uh, instead of considering the left hand side. So let us draw the free body diagram of the right hand side of this truss structure. And I have drawn the free body diagram of the right hand side. So you have to draw the entire right hand side, and you have to expose now the forces in these members HI, HB, and BC. So HI is a horizontal force because it is acting in this member, so it will going to act along the axis of this member. So BH is inclined at some angle theta. Of course, this is an angle theta. This member is making with the horizontal, and this angle is actually same, opposite angles. And so this is inclined at an angle theta with the horizontal. So the force BH is acting along the axis of member BH, and similarly the force acting along the member HC is shown here. And all the known forces are shown actually on the right hand side. So let us find the angle theta first. Tangent theta is equal to 2 by 2 because this is 2 feet and this is also 2 feet, and you can straight away get the value of angle theta, which is 45 degrees. So this angle is 45 degree. And what else you can do is that you can resolve this FBH into its components FBX and FBY. And so you already know this angle 45, so it is very straightforward to pretty simple to resolve this force FBH into its component. So FBX is FBH cos of theta, which is nothing but 0.707 FBH, and FBY is FBH sin theta, which is 0.707 FBH. And one thing uh, you might have realized that I have shown these forces to be of tensile nature, that is acting away from the point of contact. So in statics, if there is a point here and the force is applied, and the direction of this force, I'm sorry, so if the direction of the force is basically is acting away from the point of contact, it is of tensile nature. So this is a tensile force, okay. And if the uh, direction is shown towards the point of contact, then it is compressive. So you observe that I have shown all these forces acting away from their point of contact here and here. So these are all tensile, but this assumption is purely arbitrary. Okay, you can also assume them to be compressive, that is acting towards the point of contact. So now since we have the angle of the value of angle theta, we have resolved this BH. Okay, we can apply the remaining equations of equilibrium, and the remaining equations of equilibrium are summation of Fx, summation of Fy, and the moment equations. So if you will sum the forces in the horizontal direction, you will have minus Fhi, minus Fbc, and minus Fbx, because this one is acting in this direction, and the x component of Fbh is acting in this direction as well, and and this Fbc is also acting in the negative direction. So all of them are actually negative here. But this equation will not going to do any good to us, so we have to write down summation of Fy equals to 0. And for that we will be using this force of 80 pound, 60 pound, 40 pound. All of them are acting upwards, so they are all positive, and the y component of Fbh is negative. Okay. So from this equation you can directly calculate the value of Fbh, because we know that Fby is nothing but 0.707 Fbh, and so it comes out to be 254.596 pound. And Since we have assumed it to be tensile, that is acting away from its point of contact, and the sign is positive here, which means that our initial assumption was correct. This force FBH is indeed tensile in nature. So I have written a alphabet T here, which is indicating that the force in this member BH is of tensile nature. So this member is in tension, and it is supporting a load of 254.596 pound. So you can realize the importance of this analysis, because now you are getting a value, a numerical value of the force that this member is supporting. And so once you get this value of force, in any machine element or machine part, you are in this position to design its cross section by using the methods of solid mechanics. Okay, that is not actually the scope of this course and our topic, but you can realize that the first step in designing a machine member or a machine part is to have a correct value of force that it is supporting, and then you can actually design the its cross section. So we have the value of FBH, and from this section we can find the value of the force BC as well, because the section was actually passing from BC as well, right? Of course we cannot find the value of HC from this section, because our section, it hasn't actually passed from from member HC. Okay. So we can only find the values of forces uh, from which this section has actually passed. That is FHI, which is actually not, we don't want this force. FBH and FBC was important for us from this section point of view. So let's now consider the third equation of equilibrium, which is the moment equation, and we will going to sum the moment about this point H. And so you see the force FHI, the force FBH, and this 80-pound force will not going to create any moment about point H, because their line of action is passing from point H. Okay. So when the line of action of a force passes from the point where you are trying to calculate the moment, then those forces will not going to create any moment about that point, because you cannot really establish the momentum for these forces, right? Because they are actually passing from that point. So the forces that are going to create the moment about point H will be FBC, this 60-pound force, and this 50-pound force. So the moment arm of FBC about point H is 2 feet, and this is exerting a clockwise moment. So uh, this is exerting a clockwise moment. Okay, so this was the member, this was the force FBC, and the moment arm was this 2 feet. So it is actually exerting a clockwise moment, FBC multiplied by 2, and the moment arm starting from H, ending at the line of action of force CB was like this. So if you want to calculate the rotational sense of the moment of this force, you just have to uh, take this force and join it with the tail of its moment arm like this, and this you will going to do in your minds. Okay, it's an imaginary step, and then you will going to use a curl from this moment vector, moment arm vector R, to this force FBC. This is FBC. This is the force. So we have just taken this force FBC momentarily and join it with the tail of the R. So this step we have done it in our minds only, right? Just to make sure that we are using the right rotational sense for this force in our equation of moment. So indeed it's a clockwise movement, as you can see. So this is a very simple trick and a step that you can use if you are stuck and to calculate the rotational sense of a movement. You just need to join the tail of the two vectors, and you have to make sure that you do not change the orientation of the force. So if it is in this direction, you have to preserve this direction and just join the tails, and then make a curl starting from the moment arm vector R ending up at the line of action of force, and this will going to give the direction of rotational sense of the movement. So it is FBC multiplied by 2, and this force of 60 pound is also has exerting a moment about point H, and the moment arm is 2 feet, and so this 40-pound force has a moment arm of 2 plus 1.5 feet at point H, and both these are anti-clockwise movements, because you see the moment arm is this for this one, for this force of 60 pound. So this is actually exerting a anti-clockwise movement. You just need to take the 60-pound force momentarily, bring it here at the tail of this vector moment arm, and you see that this is an anti-clockwise moment. So both of them are anti-clockwise here. And this equation directly gives you the value of FBC, which is 130 pound. And you see that this is a tensile force. This is actually a tensile force. So we have assumed it to be tensile, and tensile it actually comes out. So it is 130 pound tensile force. Now what you will do is that in order to find this force HC, FHC, we have to take another section. Let's take that section to be like this, and you see that now this section is passing from this member HI, this member HG, and this member HC, which we really want, this member HB. So they are all together 1, 2, 3, 4, okay, 4 members. So we know that the section should pass from at most 3 members, right? But we realize that FBH is now a known force. You already know the value of this force. Okay? So basically this section is passing from 1, 2, 3 unknown forces, in which this force is not required, this force is not required, and this force is required. So we will going to take this section now, this part of the truss, and draw its free body diagram, or we can say that we are just drawing the free body diagram of this joint H. So this force is not required, FHI, this force is not required, FHG, and this force is known to us. Okay, we can resolve it into its into its components. That is, this is the X, FBX, okay, FBX, and this is FBY, and this FHC is required to us. So we see that submission FX will not going to do the trick for us now, because this force is actually acting at the on the y direction. So we have to sum the forces in the y direction to find out the value of this force. Also, it is just a joint, just one particle point, so we cannot use the equation of moment as well. So the only equation of equilibrium that we can use here in order to find this FHC is the summation of Fy equals to 0. And we see that this actually gives us this equation, minus Fby minus FHC is equal to 0, and this will give us FHC equals to negative Fby, and we know that Fby is 0.707 into FBH. So the value of this FBH is known to us. It was 254.596, and so therefore we get FHC as minus 179.99, which is approximately 180 pounds. And we see that now we have a negative sign here. So this negative sign actually means that this force is basically a compressive force. It is of compressive nature. So this force is coming out to be compressive, while these two forces are in tension. These two members are in tension, while this member is in compression. So please remember that in a truss structure, the uh, members that are in compression, they are always made thicker compared to the uh, members that are in tension, and this is because that the members which are in compression, they can basically undergo buckling instability. So to avoid buckling or buckling failure, we basically design the members that are in compression thicker compared to the members in tension. And so if you have studied the concept of zero force member, you can see that there are no zero force member in this truss. That is because the only joint in this truss structure that is composed of only two members is this joint E. But you see that there is a load acting here, a known load of 40 pound external load. So this exclude this joint from being the zero force members. So this entire truss structure, it does not contain any two force, sorry, zero force member. So this is how you solve truss structure using the method of section. So it's simple. You just have to remember that you have to select a section that divide the given truss structure exactly into two piece portions, and your section must not pass from more than three unknown members. More than three unknown cannot be calculated from the section. So if you have no choice and you are trying you have to select a section that is passing from more than three members, then it means it suggests that you need to take more than one section to solve your truss. So in this problem as well, if you notice that we have taken two sections, okay, so we were not actually able to retrieve all the unknowns from just one section. So the next problem is basically uh, concerned with the frame structure. As you can see here, that this structure is a mechanical structure because it is supporting the external load. Okay, but this is very different from the truss structure that we solved just right now. And so if it is not a truss structure, then it can be a frame structure and it can be a machine structure. So we have to identify where which one is this one, this structure. So you can see that this member AB is basically, you know, it has a tendency of rotation because of 900 Newton meter force moment is applied at point A. Okay, but this peg, they are calling it a peg. So this peg is actually restricting this member AB. It is restricting this member AB from rotation, and this member BC is already fixed because this is a fixed support. It cannot translate, cannot rotate. So this means that this member is not moving at all, member BC, and because of this peg, this member AB uh, is also not able to move. So this means that both these members are fixed, and frame is a mechanical structure that supports the external load, but its members are always fixed. So this means that this structure is not a machine structure, but it is a frame structure, and obviously it is not a truss structure. So we cannot use method of section to analyze it. So we need to develop some strategy while solving the frame structures as well. So let us just try to draw the free body diagram of this entire frame structure and show all the known and unknown forces on it. Okay, please remember that we need to find the reactions at the pin and at the fixed support. So here is the pin, and we have uh, two unknowns here, AX and AY, and this is a fixed support. So we have three unknowns here, CX, CY, and the unknown moment. And so basically you see that since this is a peg, okay, and it is a kind of a support that is blocking this member AB to rotate, so it is basically in contact with this member, and when the two surfaces are actually in contact, two bodies are actually in contact, then there is a normal reaction acting at the point of contact. This normal reaction is NB that I have shown here in the free body diagram, and so this angle is 45 because this angle is 45. So this is also an unknown, by the way. So we have total of six unknowns actually, you see. So we have six unknowns, and for entire frame we have only three equations of equilibrium. So if I ask you to apply the equations of equilibrium on this frame, you will, in two dimension, of course, you will have only three equations, fx, fy, and moment. And from these three equations, you cannot find these six unknowns. So we have total of six unknowns. So therefore, we have to adopt some kind of we have to develop some kind of a strategy to solve this frame structure, and the key lies in disconnecting the members. analyze them separately. So disconnect them and then analyze them separately. So in order to disconnect these two members BC and AB, we have to select the common joint, which is basically connecting these two members, and that common joint is basically this peg. So we have to remove this peg, draw the free body diagram of member AB separately, and draw the free body diagram of member BC separately. So here I have removed this peg and I have removed this pin and I have drawn the free body diagram of this member AB here. So here are the two unknown reactions AX and AY for the pin. This NB is acting at 90 degree on this member AB. Okay, and it is making an angle of 45 degree with the vertical, I know. Okay, because this is y axis and this is x axis. So if this member AB is making an angle of 45 with the x axis, it is going to make an angle of 45 with the y axis, this NB. So let us calculate the sum the moment about this point. When we will going to sum the moment about this point, I know that AX and AY will not going to produce any moment about point A because their line of action is passing from point A. So only this force will going to create moment about point A, and I already have a known value of moment acting at point A, which is 900 Newton meter. So this is clockwise, and this one is also clockwise. The moment exerted by NB. Right? You can convert 800 millimeters into meters by dividing it with 1000, and you see that you are getting a value of NB. We are getting the value of NB as 1125 Newton, but with a negative sign. So this means that the direction that I have assumed here, that is the downward direction, it is basically not downward, but it is acting in the upward direction. So I have shown the correct direction here, that it is this NB is acting in the upward direction. So my initial assumption was incorrect, and therefore I'm getting a negative sign here, and this is very important now. Okay, because since I assumed it to be downward on this member AB, it comes out to be in the opposite direction. So this is negative. I have to use now this negative sign in my calculations wherever I will going to use this NB. So now in my future calculations, all future calculations, wherever NB will going to appear, I will going to use a negative sign with it. So let us sum the forces along the horizontal direction on this member AB. I have AX plus sine of 45 into NB. This is the horizontal component of NB, and this is the vertical component of NB acting downward, right? So AX plus NB sine 45, and since NB is negative, you have to use a negative sign here. AX comes out to be 795.495 Newton, right? So you have NB now, you have AX now, we have to find out AY, and for that we need to apply the summation of forces in the Y direction. So when you sum the forces in the Y direction, okay, you have the Y component of NB. NB, remember NB was actually acting like this on member AB, so its Y component was acting like this, negative Y direction. Sorry. Yes, it's negative Y direction. That is why it is minus NB cos 45. This angle was 45. So this was 45. And AY was acting upward. So this is positive. So AY was acting in the positive upward direction. So AY is positive, and this component of NB is negative, NB cos of 45. And since NB was actually negative, I have to use a negative sign here with NB, the value of NB. So AY comes out to be minus 795.495. So I have calculated AX and AY, two of the unknowns I have found out, but I need to find out CX, CY, and the equation of moment. So I have to consider now the free body diagram of member BC. Right? So let me draw the free body diagram of member BC. I have opened this tag here. Okay, remove this member AB, and I have shown only the member BC and I have shown all the known and unknown forces acting on this member BC. And please note that when I analyzed member AB, I used a downward direction for this normal reaction NB. I used a downward direction on this member AB. So when I will going to, since this was a common connection, when I will going to use the free body diagram of BC, I have to show this member NB in the opposite direction on this member BC. And this is because when I again join this BC and this AB together, these reactions NB cancels out each other internally. Okay, because NB only appeared when we actually disconnected this member AB from member BC through this peg, right? So when you will going to combine these two members again, then these two reactions should cancel out each other. So if you are showing a direction of downward on this member AB, you have to show a direction in the opposite way on member BC. This is because of Newton's third law, right? So if this peg is, in other words, you can say that if this peg is exerting a reaction NB in this direction, downward direction on member AB, then it is going to exert the same reaction on BC but in the opposite direction. This is a very, very important point, and you have to make sure that you understand it clearly, because in solving machines and frames, you always have to do like this, because you see we have to dismantle and disconnect the members, okay, and therefore we have to keep this important crucial point in our minds. So once we have done this, we have to apply summation of fx equals to 0 in order to get cx, then summation fy equals to 0 in order to get cy. Let us do that. Okay, so summation fx equals to 0, therefore this means that cx minus nb sine 45. So this angle was still 45, and the x direction, the horizontal member of nb is acting in the negative x direction. So that is why negative nb sine 45. So when you will take this nb sine 45 on the right hand side, okay, it will become positive, but you know that originally nb was negative, so you have to again put a negative sign here, and you get the final value of cx is minus 795.495. So you see that even this direction comes out to be negative. Originally we assumed it to be in the positive x direction, but actually it comes out to be in the reverse direction. So this negative is telling us that it is not acting like this, it is acting like this. Similarly, summation fy equals to 0 will give you cy minus 500, and y component of nb is acting upward like this on this member bc. So it is positive nb cos 45, but you know that nb originally was negative, so you have to use a negative sign here with its value, and you get cy equals to 1295 newton, which is approximately equal to 1.3 kilonewton. And by the way, this time cy comes out to be positive, so this means that this direction cy that we assumed initially is correct. So now we have to find out this member, this unknown mc, and for this we need to actually sum the moments about point c of all these forces. So let us now sum these forces, sum the moment of these forces about point B, and this will going to give us anti-clockwise moment. This 500 Newton force is exerting an anti-clockwise moment about point C with a moment arm of 600 millimeters. Okay, so you can write negative moment with this force. Then similarly, this x component of nb will not going to create any moment about point C because its line of action is passing from point C. Similarly, cy and cx will not going to create any moment about point C. Their line of action is also passing from point C. But only this member, this component nby will going to create moment about point C, and its moment arm is 600 plus 600, 1200 millimeters. So nb cos of 45 into 1200, and this force is actually exerting a moment of clockwise, so that is why it is positive. And we know that at point C there was an unknown moment already acting there, mc, so you have to take that one, include that one in this equation, mc. So from this equation you see that you have only one unknown here in this equation, and its value is 1254.59 newton meter, which can be written as 1.25 kilonewton meter. So this is the unknown moment. So we have all the five unknown reactions that we wanted: AX, AY, CX, CY, and MC, the unknown moment acting at point C. So this is how you solve a frame structure. Okay, uh, it is always, you will notice that the number of unknowns will going to exceed the number of equations of equilibrium if you will consider the entire free body diagram of the frame, and this will going to make your problem statically indeterminate. Okay, you will not be able to solve it. So therefore the trick is to dismantle or disconnect the members of a frame structure, and so you have to dismantle and disconnect them from the common joint. Okay, in this problem the common joint was the peg B, and therefore once you dismember them, you can analyze each and every member separately. Okay, so for each and every member you will going to have at most three equations of equilibrium, and you can find out uh, the unknowns by analyzing the equilibrium of each and every member, because in this way you will going to have more equations, so you can find out more unknowns. So this is the trick for solving frame structures. uh, in the next lecture we're going to solve some problems on uh, machines. Until then,